Hello and welcome to another bright, shiny week of ECE 108. This week we're going to talk about binary relations, which are a special type of relation, and then we are going to discuss graphs and some applications of graphs to problems in computer science. So without further ado, let's jump right in. So recall the definition of a relation. A relation R on sets A1, A2, all the way up to AN is just going to be a subset of this Cartesian product. So previously we examined some special types of relations, namely, we examined functions. Further, we examined special types of functions, which are also relations, namely injective functions, surjective functions, and bijective functions. But we know there's relations that aren't functions, so this kind of begs the question, are there useful relations that are not functions? So the short answer to that is yes, and the long answer for that is watch lectures 15 and 16. So now, in general, relations can include lots of things. So for lectures 15 and 16, we are going to restrict ourselves to certain types of relations called binary relations. So a binary relation is a subset of A cross B for some sets A and B. Here, A and B can be any set that you can potentially imagine. So just some nomenclature. If R is a subset of A cross B, we'll say that R is a binary relation or just a relation from A to B. Now let's introduce some useful notation. So for relations from A to B where A is equal to B, so explicitly for relations from A to A, we write R as a subset of A squared for brevity rather than writing this A cross B. Further, if I have an element of a binary relation of the form A comma B, I can often rewrite this as A R B instead of using this notation. So throughout this lecture, I will swap between these two notations pretty freely, so just keep that in mind. And one more point, for the rest of this lecture and lecture 16, I will simply say relation to refer to a binary relation. So what can I do with these binary relations? So like with functions, I can define the domain, the codomain, the range, and the image of a relation. So explicitly, given a relation R that's a subset of X cross Y, I say that the domain of R, denoted by dom of R, is simply going to be the set of all X in X, so this first set here, such that there exists a Y in Y, such that X is related to Y. Now, this is essentially the same definition that we use for a domain of function, and notice that the domain of R is simply going to be a subset of X. Further, I can talk about the codomain of R, and just like with functions, I'm just going to say the codomain of R is simply this set Y. Likewise, I can define the range of R. So the range of R is going to be defined in the same way that I defined it for functions, explicitly. The range of R will simply be the set of all Y and Y, such that there exists an X and X, such that X is related to Y. Next up, I can talk about the image of a set. So if I have some subset of X, say X1, the image of that set under R is going to simply be the set denoted by R of X, and that will be the set of all Y and Y, such that there exists an X in that X1, where X is related to Y. So this is all of the things that elements of X get mapped to if I want to use my nomenclature from functions. Finally, the inverse image or pre-image of a subset Y1 of Y under R is simply going to be the set denoted by R inverse of Y, and this set will be the set of all X and X, such that there exists a Y in Y1, where X gets mapped to Y by my relation. Again, here I was just stealing the terminology that I used from functions. So far, all of this stuff looks similar to what I had before with functions, with the main caveat being I'm no longer restricted to having a single value of Y associated to any given value of X. And every value X and X does not have to appear in an ordered pair. So a natural question you can ask, and a question that many of you actually asked on Piazza, is can we define what it means for a relation to be injective, surjective, or bijective? And the answer to that is yes, we can define these definitions if we wanted to, and in some contexts they can be useful, but for our purposes, we're not going to discuss injective, surjective, and bijective relations. We're going to strictly find these terms if the relation is also a function. Now, like with functions, when you first look at binary relations, things can appear to be a little abstract on the surface. So let's look at a few examples. So let G be a subset of R2, be the set of all ordered pairs X comma Y, such that X is greater than Y. So now, given the set, I can ask you a few things. One, prove that this is a relation and give its domain, range, the image of the set 1, 2, and the pre-image of the set 1, 2. So how would I do this? Well, in order to show that this thing is a relation, I just need to show that it's a subset of R2, and that's trivial. So this is in fact a relation. Next up, if I want to find its domain, I need to think, what are the collection of all of the elements x in R such that x is associated with some y? Well, for any given value of x, there's always going to be a real number that's less than it, so every single real number will have some y associated with it. Therefore, the domain of G is simply going to be all of R. Next up, what is the range of this? So what are the possible values that I can get in this component of the elements of G? Well, for any given real number y, I can always find an x in R such that x is bigger than R. Therefore, the range of the set will simply be all of R. And in this case, the range is also all of the codomain because the codomain is R. Next up, how would I find this G of 1, 2? Well, by definition, G of 1, 2 is simply going to be the set of all y in R such that one of two things holds. Either 1 is greater than y or 2 is greater than y. So explicitly what I'm doing here is I'm plugging in this 1 in for x and this 2 in for x, and I'm asking what is the set of y's that are associated with either of these two numbers? Well, if I think about this inequality for a second, I can immediately notice that the set of all y's such that y is less than 1 or y is less than 2 is the same thing as the set of all y's such that y is less than 2. Therefore, the image of this set will simply be the set of y in R such that 2 is less than y. Next up, I can ask about this preimage. What would this preimage be? Well, by definition, the preimage of this set 1, 2 is simply going to be the set of all x in R such that x is greater than 1 or x is greater than 2. Again, I'm just plugging in this 1 and 2 into this statement here to determine all of the values of x that would be associated with one of these two elements here. So again, I do the same process. I note if x is greater than 1 or x is greater than 2, then I must have that x has to be greater than 1 for that to be satisfied. Thus, the inverse image of this set will simply be the collection of all x in R, such that x is greater than 1. Now notice that something being an element of G is really the statement that x is greater than y. So this binary relation G is really just the greater than operator being applied to R2. Note that 4, 3 is an element of G, and this can be rewritten as 4G3 since 4 is greater than 3. So kind of the TLDR version of this slide is the standard greater than operator that you apply to real numbers is a binary relation. You've seen these before. Now let's take a peek at another binary relation. Let E be a subset of R2 be the relation x, y in R2 such that x is equal to y. So we can ask the natural questions again. What's the domain of E? What is the range of E? What is E of 1? And what is E inverse of, say, pi? So here, clearly, this is a relation because it's a subset of R2, so we don't really need to do anything there. The domain of E will simply be R, since for all x in the real numbers, there exists a y in the real numbers such that x is equal to y. By the same argument, the range of E will also be all of R, since for every element y in the codomain of E, there exists an element x in the domain such that x is equal to y. And now the set E of 1 will simply be the set of all y in R, such that, well, 1 is equal to y. And what is the collection of all y in R such that this is true? Well, that's simply the set 1. Similarly, if I want to take the inverse image of pi, this will be the set of all x in R such that pi is equal to x, or x is equal to pi. Thus, G inverse of pi is simply going to be the set of pi. Now, putting all this together, E does exactly what the standard equals operator does for the real numbers. Thus, the equals operation on R2 is going to be a binary relation. Let's look at something slightly more exotic. Let A be a set, and let S be a subset of the power set of A squared. Be this relation here. So explicitly, the elements of S are elements of the form x comma y, where x and y are subsets of A, and x is a subset of y. Now I can ask some questions. What is the domain of S? And say, what is the range of S? Well, to find what the domain is, I need to ask, what sets for x can I plug into this first component here? Well, if I were to let y just simply be all of A, then it's pretty clear that x can be any subset of A. Thus, by definition, the domain of S will simply be the power set of A, since the power set of A is the set of all subsets of A. Similarly, if I wanted to find the range of S, I need to ask, what are the possible sets that I can plug in here for Y? Well, the null set will be a subset of A, and the null set is a subset of all sets. Therefore, from here, I can see that Y will just be an arbitrary subset of A, and thus the range of S will also be the power set of A. So kind of looking at the big picture, what does this really tell me? This tells me that the subset operation applied to the subsets of any set A is a binary relation. So in particular, if I let A be the universal set for whatever problem I'm working with, the subset operation that we've been using throughout this term is an example of a binary relation. Now, we know sets can be these exotic things, so let's look at some particular examples of relations on a set A that can be useful in practice. So first up, the following are relations on a set A. The null set. So the null set is a subset of A cross A, therefore the null set will be a relation on A, and this relation we will call the empty relation or simply the null relation. Next up, I can build a new relation that I'll call the equality relation. So E is going to be the set of all A comma A such that A is an element of A. So in essence, what is this relation really doing? Well, it's simply saying that for all elements in A is equal to A. Next up, we have the set U that's simply equal to A squared. This is the universal relation on A. So this is simply saying take all elements A comma B, where A and B are elements of A, and build a relation out of that. So a kind of key thing to note here, the universal relation contains all possible relations and functions from A to A by its very definition. So finally, if R is a relation on A and B is a subset of A, then I can define a new relation defined on B. Explicitly, I can define this R sub B to be R intersect B squared, and this will be a relation on B. So this is pretty clear that this is going to be a relation. So this relation has a name. We're going to call it the restriction of R to B. So a good exercise would to prove that all of these above are relations. This is pretty trivial. You just have to show that they're subsets of A cross A or B cross B for the case of this last one. Now, to end this discussion with one more example, the operations equals, greater than or equal to, less than or equal to are all going to be binary relations on Z, Q, R, and also on any subsets of these sets. So throughout the rest of this lecture and in the next lecture and doing all of your homework and in anything you ever do with binary relations for the rest of your life, I want you to think that binary relations are kind of generalizations of these operators, and they do similar things to what these operators do on these sets. So if you keep that in the back of your mind, it can help things be a little bit more concrete. Now, like with functions, there's different types of relations I can talk about. Instead of talking about injectivity, surjectivity, or bijectivity, I'm going to talk about different types of properties. So let's jump in and give you a lot of definitions. A relation R, which is a subset of x2 on a set X, is symmetric if for all x and y in x2, x and y is an element of R, if and only if y comma x is an element of R. So notice here that this notation is kind of shorthand for writing out for all x and y and x. And throughout the lecture and throughout my work, I'll probably swap between the two of these. I honestly prefer this version here, but they're mathematically equivalent and it doesn't matter which one you use. So just keep that in mind. So what is a symmetric relation really telling me? Well, let's draw a picture real quick. So here I've drawn two sets. So in particular, I have x and x. So since relations are subsets of x2, I can still kind of use the way of drawing out a relation that I used when I was considering functions. So let's just draw some arbitrary relation here. Notice that unlike functions, I don't have to have everything mapping to something. So to be explicit, here these 3 points aren't mapping to anything, and that's perfectly fine because this is a relation, not a function. Also note that unlike functions, here I have a single point that's mapping to more than one point in my codomain. That's also fine because I'm now talking about relations, not functions. So I could ask myself, is this function symmetric or not? Well, the answer to that is no, it's not symmetric. So why isn't this symmetric? Well, this dot here is related to, say, this dot over here, but this dot here, which is the same dot that I had over here, just drawn over on the other set, is not related to this dot here. So this wouldn't be symmetric because this relation here with the red dashes doesn't go the other way. Thus, if I wanted to make this a symmetric relation, I need to add in a bunch of lines. So what lines do I need to add in? Well, this is related to this, okay? So the relation needs to go back the other way, and it does. This point is related to this point, but this point over here is not related here. So if I wanted to make this a symmetric relation, I need to add in that. Next, this point is related to this point down here, but this point down here is not back related to the original point over here. And finally, this point is related here, but this point over here is not related to that. So if I wanted to make this a symmetric relation, I would have to add in these ordered pairs that I drew in red. So now you can kind of see why I'm using the word symmetric here. So explicitly, if I draw a line in the middle, there is a symmetry where it doesn't matter if I'm going this way when I'm considering my mapping, or if I go this way when I consider my mapping, the relation is the same in both directions. So that's what I mean by symmetric. Next up, I can define asymmetric relations. So a relation on a set X is going to be asymmetric if for all x and y in R2, if x and y is in R, then y comma x is not in R. So let's kind of visualize what this definition means. So going back to the same picture that I had before as kind of my sample relation, for this relation to be asymmetric, it has to be the case that whenever say one dot, say this guy here is related to this dot over here, it must be the case that this dot, just kind of transposing back over, can't be related to this dot over here. And that has to hold for all x, y in R. So we can ask a question, is this relation as I drew it asymmetric? Well, let's just kind of go from bottom up to the top. This dot is related to that dot, so okay. In order for this to be asymmetric, I need to have that there is no line from this dot down to this dot. Check. This dot is related to this dot, okay. And there is no line from this dot over to that dot, check. Further, this dot is related to this dot, but this dot is not related to that dot, check. But this dot's related to here, and this dot's related to here, so this line violates asymmetry. So now, if I draw my line again and try to think of asymmetry in terms of symmetries, you can notice that if I were to delete this red line, so let's just squiggle it out, but if I delete this red line, there's kind of a natural asymmetry between here. If something maps from here to here, then I don't also have the same mapping going the opposite direction. Namely, this point doesn't map back over to here. Now, an important thing to note, and I'll show examples shortly, you can be both symmetric and asymmetric. You can be symmetric while you're not asymmetric. You can be not symmetric while you are asymmetric. And you can be neither symmetric nor asymmetric. Explicitly, that's because I have these for all statements here. So all I need is to violate one point to violate symmetry or asymmetry. Next, we have antisymmetric. So a relation R on a set X is antisymmetric if for all x and y in R2, whenever x1 and whenever x comma y is in R and y comma x is in R, then x is the same element as y. So let's go back to Mr. Paint and visualize this. So in order for something to be antisymmetric, then it needs to be the case that whenever x is related to y and y is related to x, then x and y are the same element. So let's look at this case here. So here from our previous work, we've noticed that these connections here, here, and here are x comma y type connections, but they're not also y comma x type connections. So I don't really need to consider these. So in this case, the only kind of relation that I need to consider is this dot being related to this dot. So clearly, this dot's related to this dot, and this dot is related to this dot because it's the same dot, and thus this relation as I drew it will be antisymmetric. So how do I violate antisymmetry? Well, I could simply add in this red line here. In this case, this dot is related to this dot, and this dot is related to this dot over here, but the dots are different. So this would be a violation of antisymmetry. So now, while those graphs can help you get a good idea of kind of why we might pick these names or kind of what's going on, the most important thing to really know are these definitions and how to prove or disprove whether or not they hold. So in practice, when I work with these type relations, I never draw a diagram for them. Unlike with functions where it's kind of clear to see when something's not injective or not surjective or not a function even, that's not really the case for relations. So now that I've given you a lot of definitions, let's go through some examples to see what type of function, to see what type of relations are symmetric, asymmetric, or antisymmetric. The null relation, would this be symmetric? Well, the null relation will be symmetric if this statement here holds for all elements of the null relation. Well, there's nothing in the null relation, so this is false if and only if false, therefore this is going to be symmetric. Further, to see whether or not the null relation is asymmetric, we need to show that this statement here is true. Well, again, since nothing is in the null relation, this is false implies false, that's going to be true. And finally, to see whether or not it's antisymmetric, we need to see whether this statement is true. Again, there's nothing in the null relationship, so this is false and false implies false, which that is also true. So trivially, the null relation satisfies all three of these, and it's kind of a special cookie, because in each one of these cases, it was just trivially true. Next, let's look at the relation equals defined on the real numbers. So would this be symmetric? Well, for equals to be symmetric, whenever x is equal to y, I would need it to be the case that y is also equal to x. Is that true for real numbers? Yes, so this would be symmetric. Next, for equals to be asymmetric on the real numbers, I would need it to be the case that whenever x is equal to y, y is not equal to x for all elements x and y in the real numbers. Is that true? Well, no. So this would not be asymmetric. Finally, for equals on R to be antisymmetric, it would need to be the case that for all real numbers x and y, if x is equal to y and y is equal to x, then x is equal to y. Well, that's trivially true. Okay, so now let's look at greater than on R. For this to be symmetric, it would have to be the case that for all real numbers x and y, if x is greater than y, then y is greater than x. Well, that's not true for any real number, so there's infinitely many counterexamples for this for all statements, therefore this will not be symmetric. Now, for asymmetry, it would have to be the case that if x is greater than y, then y would not be greater than x. Well, what's the negation of greater than? That's less than or equal to. And if I have two real numbers, x and y, such that x is greater than y, does that imply that y is less than or equal to x? Well, yes. So this will be asymmetric. Finally, for this operation on the set R to be antisymmetric, it would have to be the case that whenever x is greater than y and y is greater than x, then x is equal to y. Is this true? Well, if I examine this hypothesis, are there real numbers such that x is greater than y and y is greater than x? No. So this is false. So this statement is of the form false implies false or false implies true. So this is true, but it's vacuously true. Next up, let's examine less than or equal to on R. Is this symmetric? Well, for all real numbers x and y, is x less than or equal to y true if and only if y is less than or equal to x? Well, no, right? That's only going to be true in the case where x is equal to y, so this will not be symmetric. What about asymmetry? For this to be an asymmetric binary relation, it would need to be the case that for all real numbers x and y, if x is less than or equal to y, then y is not less than or equal to x. Well, if I expand that negation, that's saying x is less than or equal to y implies y is greater than x. Is that true for all values x and y? No. In particular, I could have x is equal to y. In that case, I get true here, like x is less than or equal to x, but clearly x is not greater than x. So this relation is not asymmetric. Finally, to examine whether or not this operation on R is antisymmetric, we need to ask if whenever x is greater than y, or whenever x is less than or equal to y, and y is less than or equal to x, does that imply that x has to equal y? Well, for real numbers, that's true, therefore this will be antisymmetric. Next, let's examine one more relation. So here I'm defining a relation by a bunch of pairs. So this would be a relation from the set containing AB to the set containing AB. So explicitly, my kind of domain and codomain set is this set here. So again, A and B can be anything I want them to be. They're just two different objects. So think of them as 1, 2 if you want. So here, this relation is the relation that relates A to itself, relates A to B, and B to A, but nothing else. Would this be symmetric? Well, it's symmetric if A is related to B, if and only if B is related to A, and that's true for this relation. So this would be symmetric. Further, this would be asymmetric if A is related to B implies that B is not related to A. This is not the case for this function. So explicitly here, I have A is related to B and B is related to A, so that's sufficient to show that this for all statement is false. Next, to see whether or not this is antisymmetric, I need to show that it's the case that whenever A is related to B and B is related to A, then x is equal to y. Well, in this case, A is related to B and B is related to A, but I said earlier A and B are distinct objects. Therefore, this will not be antisymmetric. So this is kind of a counterexample where I can have a symmetric relation that is not antisymmetric. Next up, we have this final relation. A is related to B, B is related to A, and A is related to C. Let's examine which one of these properties hold for it. So for this to be symmetric, it has to be the case that for all A, B, and C in this domain set over here, that A is related to B exactly when B is related to A. Is that true here? Well, no. A is related to C, but C is not related to A, so this won't be symmetric. So for asymmetry, it'd have to be the case that whenever A is related to B, then B is not related to A. Well, this is clearly not the case because A is related to B and B is related to A, so this won't be asymmetric. And finally, for this to be antisymmetric, whenever A is related to B and B is related to A, it must be the case that A and B are the same object. Well, here, A is related to B, B is related to A, but A and B are distinct objects, so this is also not antisymmetric. So here you can see between all of these relations, there's all kinds of different relations between symmetric, asymmetric, and antisymmetric relations. So a natural question is, are there any general conclusions I can make about these different types of relations? And the answer is yes. If R is an asymmetric relation on A, then R is antisymmetric. So just briefly going back to my chart, here I see, here's a case where this is true, and indeed this is true. And in this other case, I'm asymmetric, but I'm also antisymmetric. So in these two cases, this proposition holds, this holds in general. Further, if R is a non-empty asymmetric relation on A, then R is not symmetric. So if it's asymmetric, then it's not symmetric, given that it's not empty. So let's look at this. In the empty case, this clearly is a violation, but I explicitly in my theorem say if it's not empty. But if I look at all the other cases, whenever it is asymmetric, it isn't symmetric. So that seems to hold, and it does in fact hold. So let's prove some of these. So to give a formal proof for this first one, we first say let R be an asymmetric relation on A. Well, here, since I'm dealing with sets, I need to potentially be careful with the null set. So for this case, if R is the null relation, then it's trivially antisymmetric. We proved that in the chart before. Now I can say if R is not the null relation, I can talk about things being elements of R. So if R is not the null relation, then since R is asymmetric, whenever X is related to Y, then X comma Y is not in R. So here I made a typo with the R, but that'll be fixed shortly. What does this mean? Well, if R is going to be antisymmetric, then I need to examine the proposition X is related to Y and Y is related to R. But since this statement here is true, I know this statement will always be false. Thus, when I go to test to see whether or not R is antisymmetric, I have something of the form false implies something that may or may not be true or false. Well, that's vacuously true, thus R is vacuously antisymmetric. So now, note this is kind of a proof in words. You can also do this as a proof in symbols, similar to, say, claim 31 in your text, or in the argument presented on page 53. So just keep that in mind. It's kind of a stylistic choice. So next, how do I prove this second statement here? Well, first let R be a non-empty asymmetric relation on A. So what does this tell me? So like before, this tells me that whenever X is related to Y, Y is not related to X. Thus, pretty clearly, by definition, R can't be symmetric, since for all values X comma Y and A squared, by nature of R being asymmetric, it's the case that Y comma X is not an element of R, and this violates the definition of symmetry. So explicitly, I have at least one counterexample, since R is non-empty, for R being symmetric, and that's sufficient to disprove the for all statement. Okay, so as you can see, despite the fact that that chart previously looked like we might not be able to make any type of relations between symmetric, asymmetric, and antisymmetric relations, we actually can via this theorem here. Now let's turn tables a little bit and talk about reflexive and irreflexive relations. So a relation R on a set X is reflexive if for all X in R, X comma X is an element of R. Now let's go over and talk to Mr. Paint about what this would look like. Well, here, this is the relation that I wrote earlier. So this would not be a reflexive relationship because I need it to be the case that every dot on this side points to itself or its counterpart in this other set. So to make this reflexive, I would have to add these lines. Next, we say that a relation R on a set X is irreflexive if for all X in X, X is not related to X. So let's go to Mr. Paint and look at irreflexive functions graphically. So here, just using our kind of go-to relation that I drew earlier, in order for this relation to be irreflexive, it must be the case that no dot over here points to its counterpart in this other set. So explicitly, to make this irreflexive, I have to get rid of this line here. So from here, it can be pretty immediately obvious that you can be both reflexive and irreflexive, and you can be both neither reflexive nor irreflexive. Since these are for all statements, so for them to be true, they have to be true for all values. So let's look at a few examples. So the relation null set. Is this going to be reflexive? Well, yes, since there's nothing in it. Is this going to be irreflexive? Well, yes, since there's nothing in it. Okay, let's go look at some more non-trivial relations. The equals relation on R. Is this reflexive? Does X equal AX for all values of X in the real numbers? Yes. Is this irreflexive? Is X not equal to X for all X in the real numbers? No. So this is not irreflexive. Next, greater than. Is X greater than X for any real numbers, or for all real numbers, but for any of them? Well, no, it's not true for any of them. Therefore, it's not true for all of them. So this would not be a reflexive binary relation. Next up, is this irreflexive? Well, is X not greater than x for all real numbers x? Well, x is equal to x, and the negation of greater than is less than or equal to, so this will be irreflexive. Okay, one more example, less than or equal to. Would this be reflexive? Is x less than or equal to x for all real numbers x? Well, yes, so this will be true. And is x less than or equal, and is x not less than or equal to x for all real numbers? Well, no, x is equal to x, so this will be false. So now I've seen a bunch of cases. I can be both reflexive and irreflexive. I can be reflexive, but not irreflexive. And I can be irreflexive, but not reflexive. Can I be both not reflexive and not irreflexive? Well, yes. So here I kind of contrived a relationship to make this work. So if R is a relation on X, that's defined by this subset here, will this be reflexive? Well, no, because B is an element of X, but B is not related to B. Will this be irreflexive? Well, no, A is an element of X, and A is related to A. So this is how you kind of contrive a counterexample to show that you can be both not reflexive and not irreflexive. So like before, I can ask a question, can I derive any relationship between these two properties of relations? Well, the answer is yes. If R is a non-empty relation, then R cannot both be reflexive and irreflexive. So the only case where I can have true is when R is not the empty set. So this is pretty trivial to prove, and I'm going to leave it as an exercise that I'll probably throw onto the extra practice problem set. So now I can ask another question. So now I've defined 5 different types of binary relations, namely symmetric, asymmetric, antisymmetric, reflexive, and irreflexive. So a natural question to ask is, are there limitations on whether or not a binary relation can be any of these 5 types of binary relations? And the answer to that is yes. So claim 31, suppose R is a relation from A to A, then R is asymmetric if and only if R is both antisymmetric and irreflexive. So the best way to prove this is brute force. It can be a little bit algebraic intensive, and this video is a bit long, so I'm going to leave this as a exercise for you to read the proof presented in the book. Okay, so for assigned reading, I want you to read pages 52 through 55. In this assigned reading, there are several good examples for how to think of these various relations in terms of, say, the relation between a parent and its child. So it would be good to read that bit of text there. And they also have the proof for claim 31, which you should read. So we have a meme for today. When your math teacher asks you to explain the reflexive property, x is equal to x, math is math. Okay, so that's it for this lecture, and I will see you next lecture.